Hello everyone, this is Ray Space here in Kerbal Space Program 1.12 with RSS Interstellar, that's real solar system, real exoplanets, and KSP-Interstellar so that we can go to other star systems. And in this case, I am trying to do so without warp drives, and we are exploring the different drive options that we have in KSP-Interstellar for doing this. And there is realism overall in here with all the associated mods, but I'm not really doing any realism overhaul-ish kinds of things. So anyway, RSS Interstellar it is. And in the previous video, I used the Daedalus drive to get an uncrewed ship that could take crew, but just 4 crew. And I took it over to the Alpha Centauri system, and we saw that it could do that. This is an expanded version that can contain, I guess that's, can provide for 6 crew actually. And, well, technically it has room for 65 because of the expanded centrifuge ring that we have here. It says it's a particle accelerator centrifuge ring, but apparently it's potentially got crew, though those don't actually, show up here. So we only have room for 6 here. And when we put the 6 in, we see that what we have right now is 93 years of food, 47 years of water, and 76 years of oxygen. Now that's all uneven, and that's because the centrifuge ring does have a carbon extractor, which takes out the carbon from carbon dioxide to replenish it as oxygen, so it provides some recycling of oxygen, and also a water purifier. So that takes the wastewater and turns it back into water. I've taken a look at the numbers for them. If they all work exactly as they should, we get back about half the water, so we only have to carry half basically, and then a certain percentage of the oxygen, though I've probably played it safe on that one, and that results in being able to have less of the life support supplies and still managing to supply 6 crew. But we have a larger ship that is going to allow us to get to Proxima Centauri, where there are planets, quicker than in the previous video. In the previous video, we went there went to Alpha Centauri in about 110 years. We don't want to do that again. We don't really want to do 93 years either, which is what I'm aiming for here. But this ship, in the previous video, we went 12 million meters per second. And this ship, I want to go 18 million meters per second. That's the goal here. And of course, if you go 18 million meters per second, you also have to slow down by 18 million meters per second, which is why we have more than 36 million meters per second. And the way we have done that, we've kept the Daedalus engine as is, because if you scale it up, it's more dry mass, and that's bad too. But we have added drop tanks of various kinds. And so there's 3 stages. First, vertically placed pair of drop tanks filled with fusion pellets will separate off. Those initially provide the 6.6 million, and then the horizontally placed ones provide the 12 million, and then the centerline ones provide the nearly 20 million that you see there. And that's mainly for slowing down. So that's the arrangement that we have, but you notice diminishing returns as we continue to add tanks here, and that's unavoidable. So we can't keep piling it up, because it all depends on the specific impulse of the engine, and even though we have 1.5 million seconds of ISP here, because we're trying to go to another star system, we're still constrained, and we still have to worry about optimal staging. What is optimal staging? Well, optimal staging is making sure that the stages provide a delta V equal to the exhaust velocity of the stage. The exhaust velocity of the stage is roughly 10 times the ISP here. It's actually 9.81 times the ISP. And so what it is 15 million meters per second would be the exhaust velocity. And so each stage, the optimal would be 15 million seconds of ISP, 15 million meters per second. And I've sort of been close to that with the first 2, but again, we can't do too much. We'd have to have huger tanks, and also the thrust weight ratio would go down even more. here it's not too bad. We're getting all this done in basically a year. So that's nice. So basically half a year burning. Well, actually it's more on the front end. So it's 2/3 of a year burning to get there, and then 1/3 to slow down, more or less. So that's this ship. But we're not getting there as fast as I would like to. Unfortunately, we have limited options. You would think that, oh, well, we've got all this advanced technology, fusion and antimatter. Surely we have a lot of options, but when you get into the 1 million seconds of ISP range, even KSP Interstellar is not replete with options. Hundreds of thousands of seconds of ISP, sure, but not millions. And in fact, aside from this, we've got the Bussard ramjet, and forgive me, I often can't find things because some of them have quotes around their names, so they're not properly alphabetized. The Bussard fusion engine is good. And we'll tackle that one in the next video. So that's 2.7 million seconds of ISP, it says, but it's got weird things like propellant solid hydrogen. I like my fusion pellets, frankly. So I don't know what to do with that. And then we have to suck in the hydrogen from the interstellar medium and convert it to solid hydrogen, and that's how that works. So that's complicated. But perhaps even more complicated is the radiant drive, which is what we see here. But when it comes to ISP, you can hardly beat it. Short of the warp engine, it promises the highest ISP at 20 million. So it's more than 10 times more efficient than the Daedalus engine, and that is because it uses antimatter. It also seems to use liquid hydrogen, and one problematic thing is it's an antimatter engine, but it doesn't say much about the antimatter usage here, does it? Well, let's take a look at the mock-up I've cooked up and see what that looks like. Front end wise, it's all the same. I can't scale up the particle accelerator centrifuge ring anymore, otherwise I would. Well, okay, it goes to 5.05 meters apparently, but this is as big as it gets basically. I like it though. Anyway, but we have the radiant drive in the back, and again, when we talk about optimal staging, well, it's got 20 million seconds of ISP, so the optimal stage for it would be 200 million meters per second, right? 10 times that. I've gotten this to 160 million meters per second. So that part's fine. In fact, it's a much smaller ship than the previous one because we only have one stage here right now, and it's at 5,000 tons, which, that means that this whole thing is the same mass as Starship Super Heavy, okay? So it's not, tonnage-wise, it's not crazy. Antimatter-wise, it's a little bit crazy. Also crazy is it says 382,000 years to do this. Now, is its thrust really that low? Well, it says here max thrust is 4,400 basically, and that's not that much less than the Daedalus engine. Daedalus engine had 8,000 or so. So what gives? It seems like this is lying to me, but how much is it lying to me? What is it lying to me about exactly? Well, let's find out. I'm not going to put crew on here. We're going to cheat up into space and see what it actually does. Now, I have not configured the radiant drive for Pekka's time warp mod so that we can use the drive during time warp, but if it takes a 6-digit number of years in order to do the burn, we don't really care. As we're not going to do that. So let's see what it does. So SAS on, throttle, ignition. Oh, now it's 4 digits. Okay, but spooling up. Alright. So 3 years, which is still longer. And boy, those radiators are getting hot quickly. Okay, extend, extend, extend. Okay, the waste heat is going down. Okay, so we didn't have a tragedy there. Apparently it's enough radiators, though I think they're gonna clip into each other. I need to make them smaller, which I guess is possible since the waste heat is going down. The antimatter ring is here, by the way. And right now it's storing a maximum of 523 grams of antimatter. So that ends up being, each unit of antimatter is a milligram. And we need a very big ring to store that half kilogram of antimatter. But the problem is it's going down really fast. So the stage time here, 3 years and 301 days, it isn't good. Because it's only judging from the liquid hydrogen load that we're carrying, but it's not judging from the antimatter load. And we're going to run out of antimatter very quickly. Now, is there something we can do about that? Well, we can reduce the reactor power. And so you can see, well, if we have a reactor that's only going at 10%, it's consuming 10% of the antimatter. Interestingly, that does not cut down on the thrust, and it doesn't cut down on the delta V that's stated. It does increase the liquid hydrogen consumption, though. So, what does this mean? I'm not entirely clear. It's increased the stage time to 38 years. I think it must have cut down the specific impulse, but it doesn't say so. It says the specific impulse is the same, then the thrust is the same. Is there another way I can... But then the stage time going up means that it cut down on thrust, right? But then it's consuming 10 times more liquid hydrogen, which means that that should be the ISP. So, numbers are not working out for me here. Numbers are lying. Some number is lying here. So let me see if I... Okay, well here it says the thrust weight ratio goes up and goes down. So that means that it is a lower thrust weight ratio here and so lower thrust. So we're not actually getting the 4,400, we're getting 400 kilonewtons. In theory, yeah, that's what that's saying for MechJeb. But then we're consuming 10 times more liquid hydrogen. You see here, oops, 0.29 per second, and then I throttle up, it's only 0.03 per second. Which seems like it's the reverse of what we would expect. We would actually expect it to be less down here and more up here because of the thrust. This is very weird. And the point is, we're not going to get the 160 million meters per second, are we? It's basically colliding the antimatter with the hydrogen, and that's it. It's making a big boom and shooting it out the back. It's underplaying the boom aspect of what would happen when you smash the hydrogen and antimatter, because it's a laser core antimatter engine, I guess, and that makes it smoother. Okay, and yep, it did not even get to boom level. So not good. Definitely not 160 million meters per second. So this is why I started with the Daedalus engine. At least it gets us somewhere. So we need more antimatter then, right? That's the idea. We need maybe less of the hydrogen and more of the antimatter. We need basically the same mass of antimatter or quantity or something as hydrogen. But you see, to store 523 grams of antimatter here, we need a part that's 52 tons. So the part mass, the dry mass, is however many, 100,000 times? 100,000 times, I think, the mass of the actual antimatter. So right there, that's 40 kilograms of antimatter. And it's really hard to plan this out because, well, that's 40 kilograms, and then, but we've got 1.4 kilotons right there. How does this all work? And boy, does it not make me happy that the actual ring has so few polygons and such a bad texture. That's just rubbing it in right there. I know what you're asking. Do we have something better to contain antimatter? That's a good question. We do have an antimatter collector, but how well can it collect antimatter? Okay. So we're collecting antimatter right into our centrifuge ring. The problem is that this says harvest antimatter from planetary magnetospheres. The rate at which the antimatter is collected depends upon the magnetic field strength of the planet. But that means we need to be around the planet, right? As we get into the interstellar medium, we're not going to have a magnetosphere in order to collect the antimatter, as far as I know. And the goal of this would be to reduce our dry mass and scale the big ring down, because if we can collect along the way, we don't need this big thing with a part mass of 4,000, which is most of the non-propellant vessel mass. So can we do that though? Can we scoop antimatter? Is this enough antimatter scooping? There's a positron factory and an antiproton factory. Production of antiprotons. But what does it need to produce them? How do you have a factory? Now we have a centrifuge ring apparently. But what goes into an antimatter factory? Well, we're gonna slap one of those on too. But we're gonna put everything on. That is a diamagnetic antimatter container. There were older antimatter containers too. I don't... Oh, this diamagnetic one is better. This is a cheaty antimatter container. Here, the part mass is only 62 tons and we're carrying... But that's anti-hydrogen. Okay, but we need antimatter, right? I don't know if that engine back there can work with anti-hydrogen instead of antimatter. Yeah, like it has to be called that, I'm not sure. Well, I mean, is there a fuel switcher back there? I mean, why is anti-hydrogen nicer than antimatter? Well, let's have that as our main antimatter containment. And see if that works, because it's so much lighter. But it feels cheatier though, right? We don't want cheaty antimatter containment. There's a reason why the antimatter containment is so heavy, because it's hard to contain antimatter. There's a nicer part though. It has more polygons than that ring. So that's a good thing. Okay, so we've got a scoop, we've got a factory. Let's see, there's this IXS antimatter collector. Adrift in space. This one is just adrift in space. So maybe it's more efficient. Deployable antimatter collector. Oh. Well, that's fancy. It doesn't look like something that's gonna collect the antimatter very quickly though, does it? But it's fancy. I don't know which one is better. Is there a number that's associated with these things? This one only requires 4 kilowatts by default. But none of them actually says how quickly they will collect antimatter. So we're putting on all of them. Okay. Let's see. Just watch it all explodes as soon as I get out there. Antimatter G-force. It doesn't like being down here. Let's just, No, don't make it go critical. Oh, okay, it exploded. Okay, let's try and get it to space much faster. Apparently have 25 seconds. Okay, set orbit, set orbit, set orbit. Uh-oh, that thing is still overheating. Okay. Now maybe it's okay. But our orbit is 0. Come on. Alright. So here... We're not really holding steady, are we? Oh, I didn't fill it up with antimatter, but okay. Let's see. Start charging? I don't know. Activate magnetometer? No, start charging. This one's collecting. But the rate is 0 mg per hour. This one's got anti-hydrogen, but will it work with this? I mean, anti-hydrogen is a kind of antimatter. I think it's working. Is it taking it is taking the anti-hydrogen. And it's taking the anti-hydrogen at an equal rate as the liquid hydrogen, instead of way higher. So when I throttle down here, it still uses less of the anti-hydrogen and more of the liquid hydrogen. That doesn't change the efficiency. So somehow using anti-hydrogen with this engine is better. The containment is easier, and it overall gets better efficiency. Well, I mean, but we're talking about 22 tons of it. Maybe it's not that much better. I mean, it's a very expensive amount. And also, our ability to collect any antimatter seems weak. This one's going at 0.0000 milligrams per hour. There's some flux here, but not much. This one is basically doing the same. This one is basically doing the same. I mean, 0.0. So we really can't do that. And how about this factory? Well, the start charging, I clearly don't have enough here. Produce on, yeah, okay. Now it's producing. But it's producing nanograms per day. 6 nanograms per day. Maximum power capacity 54 gigawatts. It's taking 54 gigawatts to produce 6 nanograms per day. How much are we using? Well, more than that per day. Definitely more than that per day. I don't even know how much delta V, but we can figure out how much delta V we actually have here because the anti-hydrogen and hydrogen are being used at equal rates. So let's go back to the VAB and size this so that we have an equal amount of liquid hydrogen and anti-hydrogen, which, you know, when you think about it, makes sense, and then see what we get, or the SPH, I mean. So I'm just gonna take this tank off and then make more of these. And then scale them up. 630,000 times 4, I mean, that's just about 2.5 million. For the first time ever, hydrogen is looking very dense compared to another propellant. That's because it takes a lot of room to store your average bit of antimatter, huh? Well, we'll still probably need the radiators, judging from how everything seemed to overheat otherwise. Okay, how much is it? Can you guess? Well, 14 million meters per second, which is not bad, right? But we're gonna need to make this a lot bigger. I mean, the dry mass is 2,300 tons for start mass of 2,500, let's call it. So, yeah. We're gonna need to make this a lot bigger to really get the best out of this radiant drive. Let's just take it outside. Let's take off the extra stuff. The scoops, we can't scoop anything. I don't know. Maybe, yeah, I have no idea how to scoop stuff under the circumstances. Not fast enough so that we can carry a smaller amount of containment. And the anti-hydrogen isn't what we're scooping with those anyway. I think we could probably change it though. Alright, taking it outside. Uh-oh, everything was overheating. No, extend, quickly. Okay. Yeah. Containing antimatter. Dangerous stuff. It starts with a rotation for some strange reason too. So now you can see we have roughly the same amount of liquid hydrogen, anti-hydrogen. Overdid the liquid hydrogen a little bit, but you know, they could be boil off or something. So it looks like it can deliver 17 million meters per second in 93 days. And with all the scoops and such off, we're down to 2,100 tons. So that's not much. That's a pretty good ship. We could launch it on the Monument launcher even. Which does bring up another question. Which of the advanced propulsion systems are actually safe for launch from Earth? I mean, probably we don't want to use this, as its exhaust will probably drill a hole into the surface right through or something. I don't know how it all works, but presumably lighting an antimatter engine on the surface of Earth is a no-no. I don't even know how you contain it like this, but yeah, need to work out which launch systems, which engines we can use for launch that people will not protest about. It's another thing. Sure turns slow. You know, if I go full up here. So 93 days. We would have to make these tanks a lot larger in order to really make this work, to get us a higher percentage of the speed of light on a trip to Proxima Centauri or another star system. But we can do that. So the key thing is that we have whatever hydrogen tank we have, but these anti-hydrogen tanks that are diamagnetic antimatter containers are much more forgiving than the other antimatter containment units. Except that they want to blow up when you take them outside. So you'll have to make sure you've got enough radiator capacity. That is the situation with the radiant drive. So the 20 million ISP, not all it's cracked up to be, but still it promises a lot. we could still use it. The other thing is the Bussard ramjet, and I'll take a look at that next time, and then we'll decide which one to use for a gigantic colony ship, which will have to be pretty darn big. 6 Kerbals is cute and all, but we are not going to be able to set up a good colony in another star system, and that's basically what we're talking about if we're going to travel many decades. So with that being the situation, this is the radiant drive, and let's get Earth in a little better of a position. There we are. And with that, thank you for watching. Hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.